Okay, so this is number 40 in your book on page 44. And the problem says the half-life of radioactive cobalt is 5.27 years. Suppose that a nuclear accident has left the level of cobalt radiation in a certain region at 100 times the level acceptable for human habitation. How long, okay, key word, how long will it be until the region is again habitable? And it says ignore the probable presence of other radioactive isotopes. So we're definitely dealing with the half-life here, and there's a lot of information. So the half-life of radioactive cobalt is 5.27 years. So again, a lot of words here, so let's translate some of those words into symbols. We know definitely that we're dealing with exponential decay here. So the solution to write some differential equation is going to be, and this is on page 40 of your book, the mathematical model. It's going to be n of t equals n naught, right, e to the kt. Okay, that's our solution, and our k here is going to be negative because this decays exponentially, or the cobalt, we want it to decay. So let's translate a couple other pertinent information. The second sentence says, suppose that a nuclear accident has left the level of cobalt radiation in a certain region at 100 times the level acceptable for human habitation. So at 100 times the level, so we definitely know n of 0, right? This is when t is 0. At time 0, we're starting with 100. And I mean, this is really 100 times 1, right? But we don't have to write the 1. Now remember what the problem is asking. It's saying, it's asking, well, how long, okay, will it be until the region is again habitable? So again, we're given lots of information, right? This is our given, right? But what's our goal? Okay, and our goal is to find t, right? How long? So we want to find t in this. Okay, so we have given and we have our goal. And, oh, I think we actually do have another piece of given information, which I forgot to write. So we also have, we're dealing with half-life, right? And remember, half-life, or half-life tau, of a radioactive isotope, right, is the time required for half of it to decay. So we definitely have, so this is part of the given, right, we have n of 5.27, right, and we started with 100, so, you know, n of 5.27 is 50, right, because we want to know when half of it, how long is it going to take for it to be 50. Okay, so let's start solving this. Okay, so let's go back to our model. And this is our exponential decay model. So let me go ahead and just write it again here. So n of t equals n naught e to the k t. And we know, right, we know this information, so n of 5.27, right, that should give me 50. So let me go ahead and just write that out. But we know this is really equal to our n naught e to the kt. Let me just move this up. So this guy, right, okay, we know is 50, so we can just say 50 equals, well, what's our n naught? We initially started with 100. E, well, to the kt, our t is 5.27, so that's going to be k times 5.27, right, or 5.27 k. And our goal is to solve for k, right, and our k, again, should be negative because it is exponential decay. And yes, that's what we said. And so this is pretty easy, right? We can, if we want, we can divide both sides by 100, right? And if we do that, we just get half, right? Which should be familiar because we know it's going to be ln of 2 eventually. So half equals e to the 5.27k. And let's see, continuing. So we can take the ln of both sides because we want to solve for k. So ln of a half, ln of e to the 5.27 k, and ln of a half, right? And we can write 0.5 if we want. And we know ln and e, right? That's just going to give us 1. And right, this is a logarithm, so I can bring down that power, which is 5.27k. And now we can definitely solve for k, which is ln, right, of a half over 5.27. And if we just get our calculators, right, and we input that into our calculator, let's see, let's round to 3 decimal places. So it's definitely going to be negative 0.1, that's a point, 1, 3, 1. Okay, so we found our k. Okay, great. But what was the problem asking? The problem was asking for t, right? So let's solve for t now. And so the model we're going to use, right? So we want to solve. Our equation is going to be 1 equals, right, our initial, I'm using my n of t, 100 e to the negative 0.1, we can even say 3, or if you wanted to put 1, times t, right? So now let's solve for t, so we can definitely divide 100 from both sides. E raised to the negative 131, that's a t. And I can definitely take the natural log of both sides. So if we want to even write it up here, so ln, and so I have, so ln of 1 over 100, okay, we'll just leave it in blue, and we know ln and e are inverse functions, so we're working with logarithms, so I can definitely bring that power down, t. And so to solve for t, right, this is just going to be ln of 1 over 100 divided by, we know this is going to be negative 0.131, and then we can punch that in the calculator. And we get, whoops, 35.4, right? That's what our t is. And so again, what was the problem asking? How long will it be until the region is again habitable? Well, after 35.4 years approximately.